Time and space are like a fabric, like rubber, like a trampoline net. Turn this trampoline net into a pretzel and allow yourself to go backwards in time.
Have you ever contemplated the mysteries that might be concealed in the vast cosmos? Consider the astonishing revelations that could potentially reshape our understanding of the universe. Picture the eminent American physicist Michio Kaku introducing a groundbreaking discovery. This revelation, brought to light by the legendary James Webb Space Telescope, has the potential to challenge the concept of time as we know it. Get ready for an exploration into a cosmic enigma that could completely shift your perspective. The James Webb Space Telescope, often seen as the more advanced counterpart to the Hubble Space Telescope, was launched on Christmas Day in 2021. This remarkable telescope has taken up its position in space, uncovering hidden secrets from the farthest reaches of the universe. It can be likened to the ultimate time machine, boasting powerful infrared instruments that allow us to peer into the past. The telescope's extraordinary resolution and sensitivity enable it to detect incredibly ancient and faint objects that were previously beyond Hubble's capabilities. These include distant galaxies and celestial bodies from the universe's infancy, entities that have eluded our observation until now. In essence, the James Webb Space Telescope is aiding us in assembling the grand cosmic puzzle, piece by piece, through its mesmerizing infrared images. Imagine strolling through an art gallery where you're surrounded by magnificent images captured by the James Webb Space Telescope, also referred to as JWST. The visuals are breathtaking, showcasing distant galaxies sparkling across the cosmic canvas. Yet, amidst the astronomers and cosmologists present, you can sense their astonishment and disbelief. It's as though they're gazing at a Picasso in a room filled with realist paintings. The prevalent sentiment among them is encapsulated by the phrase, "This is unexpected." But what's causing this commotion? What has shaken the very foundation of their comprehension of the cosmos? Though the official reports are vague, the real point of contention lies with a theory deeply cherished by these experts, the Big Bang hypothesis. This theory proposes that our universe originated from an immense explosion approximately 14 billion years ago and has been expanding ever since, like an inflating balloon. This hypothesis has been a cornerstone of cosmological knowledge for years. However, the new imagery provided by JWST appears to cast doubt on its validity, sending shockwaves throughout the scientific community. You can almost envision Alison Kirkpatrick, an experienced astronomer from the University of Kansas, grappling with doubts and questioning her lifelong dedication to her work. Why are these scientists so taken aback? Well, the galaxies captured by JWST are not behaving in accordance with the expectations of the Big Bang hypothesis. They appear too diminutive, excessively uniform, exceedingly ancient, and their sheer number defies explanation. Let's tackle the issue of their size, for instance. According to the Big Bang hypothesis, as galaxies move farther away from us due to the universe's expansion, they should appear larger, not smaller. After a specific point, they should start appearing larger because the light from these galaxies supposedly departed when they were closer. This concept is a peculiar yet essential twist within the expanding universe theory. However, the images obtained from the JWST display galaxies that are roughly the same size as those near us. It's analogous to expecting distant friends to appear as tiny specks on the horizon, but instead, they are right beside you, just as substantial as life. Interestingly, these images depict galaxies appearing smaller than what we would anticipate, even considering their greater luminosity and mass compared to our Milky Way. These galaxies appear to be 2 to 3 times smaller than those observed through the Hubble Space Telescope, HST, despite having higher luminosity and mass. Additionally, these galaxies exhibit significantly higher redshifts, indicating that they are supposedly moving away from us at faster velocities. This inconsistency was pointed out by some scientists back in 2014 when they analyzed HST images. They found that galaxies with redshifts up to 5 seem to align with what one would expect in a non-expanding typical space. The JWST was expected to continue this trend, and indeed it has, even for galaxies with redshifts as high as 12. To put it simply, the images captured by the JWST show galaxies that appear to be the same size as those in proximity to us. This challenges the notion of an expanding universe, making redshift seem more like a function of distance rather than an indicator of expansion. However, if we adhere to the Big Bang theory and the concept of an expanding universe, we are left with a perplexing conclusion. These distant galaxies must be unimaginably small to counteract the optical illusion caused by an expanding universe. This is analogous to imagining a grain of sand radiating light as brightly as a spotlight. Take, for instance, a galaxy named GHE2 that the JWST observed. It shines much brighter than the Milky Way, but is calculated to have a radius of only 300 light-years. In contrast, the Milky Way's radius is about 50,000 light-years. This means that its brightness per unit area would surpass that of the brightest galaxy in our local universe by 600 times. Moreover, the density of GHE2 and several other newly observed galaxies would be tens of thousands of times higher than the galaxies we observe nearby. When you factor in these exceptionally small and smooth galaxies, the concept of an expanding universe, including the Big Bang theory, starts to face challenges. These findings have stirred up a significant amount of discussion among astronomers and cosmologists. Over the years, the Hubble Space Telescope's images have presented difficulties for researchers, as they depict galaxies that are dense and powerful, much like the cartoon character Mighty Mouse. With the introduction of the James Webb Space Telescope, understanding these peculiarly small galaxies has become even more complex. Theorists have put forth an idea to explain these small galaxies. They propose that these microgalaxies collide over billions of years, merging together to form the full-sized galaxies we see today. It's comparable to toy cars colliding and growing into real SUVs. However, the JWST's close examination of these galaxies hasn't revealed signs of such collisions. Colliding galaxies would likely exhibit visible damage, much like a car after a crash. Yet, the JWST shows galaxies that are smooth and neat spirals, much like the ones we observe nearby. This lack of evidence for galactic collisions contradicts the collision theory. In fact, one study titled Panic highlights that there are far more of these pristine spiral galaxies than theorists had predicted. This abundance of undisturbed galaxies challenges the collision theory even further. It's akin to finding a busy highway with speeding cars, but no accidents. This contradiction to the collision theory indicates that these galaxies might not have expanded into their larger counterparts and may have been substantial from the start. This weakens the optical illusion expected from an expanding universe, which casts doubt on the expansion concept. This has left supporters of the Big Bang theory concerned. The appearance of these small, smooth galaxies suggests that the universe might not be expanding. If this is the case, the Big Bang theory faces significant challenges. Furthermore, if these galaxies existed before the proposed Big Bang event, it could mean that the Big Bang didn't occur at all. This could revolutionize our understanding of the universe's origins. The James Webb Space Telescope is like a time machine, allowing us to peer billions of years back into the cosmos. It captures images that provide insights into the universe's beginnings. Despite not capturing images in the familiar visual spectrum, the JWST focuses on the infrared, revealing the colors of galaxies that are too distant to be observed with the naked eye. These colors tell a story about the age of stars in these galaxies. Young, fiery stars appear blue, while older, cooler stars akin to our sun radiate in shades of yellow and red. Astronomers can estimate the age of star populations in these distant galaxies by examining these colors. According to the Big Bang Theory, the galaxies farthest away in the JWST images represent a cosmic snapshot from around 500 million years after the universe's birth. However, some of these galaxies appear to host stars that are over 1 billion years old. Now, if you've been following the Big Bang Theory, you know that's a significant issue because nothing should be older than the Big Bang itself. Another expectation, if the Big Bang Theory is correct, is that as we look farther into space, which means peering further back in time, we should see fewer and fewer galaxies until we reach a point where there are none, a cosmic dark age, if you will. However, it appears to be a different story. Galaxies as massive as the Milky Way seem to have been quite common even a few 100 million years after the supposed Big Bang. The new images indicate that there are at least 100,000 times more galaxies than predicted at high redshifts, more than 10. So, the question arises, how could so many large galaxies form in such a short time? The answer is they probably couldn't, at least not within the constraints of the Big Bang Theory, and that's why these discoveries are shaking the foundation of our understanding of the universe. Furthermore, there's intriguing information suggesting that the Big Bang Theory might be off the mark on multiple fronts. Recent research suggests that the Big Bang Theory gets 16 predictions wrong. Surprisingly, the only prediction it gets right is the abundance of deuterium, a type of hydrogen. But it doesn't end there. This theory, which we've held on to for years, predicts double the amount of helium and 20 times the amount of lithium that we actually find in the universe. Moreover, the Big Bang Theory struggles to explain the existence of massive structures in the universe. According to the theory, these structures are simply too large to have formed since the universe's inception. Additionally, the theory encounters difficulties when predicting the density of matter in the universe. And here's an interesting fact. Those supposedly non-existent asymmetries in the cosmic microwave background? Well, they do exist, which presents something of a cosmic plot twist. So, where does all of this leave us? Enter the James Webb Space Telescope. This remarkable technological achievement might just hold the key to unraveling these cosmic contradictions. While these discrepancies might seem like minor details in the vast landscape of cosmic knowledge, they are anything but negligible. Each minor error is akin to a missing puzzle piece, obstructing the big picture and leaving us with an incomplete understanding of the universe's nature and origins. These anomalies bring into question everything we thought we knew about the formation and evolution of the cosmos. They challenge our understanding of cosmic structures and the very fabric of space-time. This, in turn, influences our comprehension of universal expansion, gravitational waves, dark matter, and even the ultimate fate of the universe. For instance, if the density of matter is inaccurately predicted, it could alter our perspective on how galaxies form, evolve, and the role of dark matter. Similarly, the unexpected asymmetries in the cosmic microwave background could impact our knowledge of the universe's initial conditions and its rate of expansion. In fact, these inconsistencies even cast doubt on our understanding of time itself. Our current perception of time is intertwined with the universe's evolution since the Big Bang. If the Big Bang Theory falls short, we may need to re-evaluate how we conceptualize time, its flow, and its relationship with space. Consider this. These findings could herald a paradigm shift in our comprehension of space-time, akin to when Einstein introduced his theory of relativity. We could be on the cusp of a fresh understanding of the cosmos, where we must recalibrate our cosmic clocks and redefine our cosmic compasses. The universe, it seems, still holds surprises that challenge our established notions. Have you ever pondered whether time, as we understand it, truly exists, or is it merely a human-made concept to delineate past from present? It's a weighty question, no doubt, but bear with us. There's a theory suggesting that time is an illusion woven from our human memories. This theory proposes that everything that has happened or will happen is occurring right now. It's a somewhat peculiar notion, isn't it? Let's delve deeper into this concept. You might assume that time naturally flows forward. However, here's an intriguing twist. The laws of physics don't explicitly demand such a unidirectional flow. They work just as seamlessly whether time progresses forward or backward. This idea aligns with the Big Crunch theory, which posits that as the universe completes its expansion and begins to contract, time could potentially reverse its course. As the universe contracts, it heats up, creating a sort of reverse Big Bang. The question naturally arises, what follows the Big Crunch? It's a query that has intrigued many. Some theories propose the emergence of a new universe through another Big Bang, while others suggest our universe might reappear in an entirely different location, akin to a cosmic bubble popping into existence. There are even theories proposing a cyclic repetition of these events, leading to the creation of countless universes. This notion of time flowing in either direction, forward or backward, has prompted some scientists to consider a striking notion. Time itself might be an illusion, as we understand it is just a human construct. They argue that we live in a block universe where space and time are interconnected, an idea supported by Einstein's theory of relativity. In this scenario, all events, past, present, and future, have their own coordinates in the four-dimensional space-time. What does that mean for us? Well, it suggests that everything is as real as the present moment. The past and the future are still out there, existing somewhere in space-time. MIT physicist Max Tegmark explained this concept beautifully. He said, "We could view our reality as a three-dimensional place where stuff happens over time, or a four-dimensional place where nothing happens. Everything just is. If it's the latter, then time is an illusion because nothing really changes. Everything, past, present, and future, is always there. It's certainly a lot to wrap your head around, but isn't it fascinating to ponder such questions? It shows just how frighteningly magical and mysterious our universe truly is." Then we have Julian Barber, a British physicist who has quite an intriguing perspective on time. In his view, our reality is a sequence of distinct now moments, like individual snapshots. Imagine flipping through a photo album where each picture is its own unique now. That's essentially how Barber views the universe. Barber argues that our perception of the past is simply a construct of our brain's memories. That is, we only feel like we have a past because we have memories of it. The actual concept of the past, according to Barber, might be an illusion. He further elaborates on this concept through his spatial theory. In this theory, each now moment exists in a place within a vast landscape which he whimsically calls Plutonia. Every point in Plutonia represents a now, and this landscape itself follows perfect mathematical rules, making it timeless in nature. This perspective connects back to a much more familiar name, Albert Einstein. Einstein's theory of space-time is central to our current understanding of the universe. However, its implications and our comprehension of it have sparked some critical questions. What if Einstein's space-time concept was erroneous? Could discarding it entirely provide us with a clearer comprehension of the universe? This idea may seem startling, but it's important to understand that the realm of science thrives on such revolutions. Theories are continually being challenged, refined, and sometimes entirely replaced. It's through this perpetual cycle of inquiry and discovery that science progresses. A look back into history would show us how this process has unfolded over time. The geocentric model, which posited Earth as the center of the solar system, was widely accepted for over 1,000 years. Then came Nicholas Copernicus, who proposed a radical idea that Earth is just another planet orbiting the Sun, eventually replacing the geocentric model. After Copernicus, Isaac Newton introduced a new understanding of gravity. He proposed that all objects with mass have a gravitational attraction towards each other. In this framework, the reason Earth orbits the Sun and the Moon orbits Earth is because of their mutual gravitational pull. Newton's gravitational theory held sway for around 3 centuries. Then, in 1915, Albert Einstein presented his general theory of relativity, which redefined our understanding of gravity and space-time. Einstein suggested that massive objects like the Sun cause a curvature in the four-dimensional fabric of space-time. Earth orbits the Sun because it follows this curve, which we perceive as a gravitational pull. The transition from a geocentric model to Copernican heliocentrism, from Newtonian gravity to Einstein's general relativity, highlights the evolving nature of scientific understanding. Despite the solid foothold of Einstein's theories today, physicists continue to question, investigate, and push the boundaries of our understanding of time in the universe. Einstein's space-time theory has held its own for over a century, fending off all challengers. A significant victory for it came in 2015 with the detection of gravitational waves. However, no theory is immune to challenges. One significant issue arises when Einstein's general relativity, which includes the concept of spacetime, comes face-to-face with quantum physics. The two seem to operate on entirely different rules, and this creates a bit of a problem. In the quantum realm, things get a bit quirky. For instance, a single particle can exist in two places at the same time. Erwin Schrödinger famously illustrated this with a thought experiment involving a cat, a poison vial, and a quantum particle tied to a hammer. The hammer's action, whether it breaks the poison vial or not, depends on the quantum state of the particle. The catch: until we measure it, the particle is in both states at once, implying that the cat is simultaneously alive and dead. We might need to take a step beyond Einstein's idea that space-time is a smooth, continuous fabric. Einstein viewed space-time as a sort of stage, a backdrop that would exist even without the actors, the stars and planets. But as we delve into the world of quantum gravity, we may need to fundamentally rethink this concept. It's as though we're not just changing the script, but the stage itself. Laurent Friedel, Robert Lee, and George Hermannick, three forward-thinking physicists, are shaking things up. They argue that the way we think about space-time might be limiting our understanding. To them, space-time doesn't exist separately from the things within it. Rather, it's defined by the interactions between objects. This flips the script, suggesting that space-time isn't something that needs to be merged with the quantum world, but that it actually emerges from the quantum world itself. It's a shift in perspective that's as groundbreaking as it is precise. This new take on space-time theory could be the key to solving a notorious conundrum in theoretical physics, the mysterious entanglement phenomenon. This is a situation where two particles are so intimately connected that a change in one triggers an instant change in the other, no matter the distance between them. This seems to violate relativity, as it's like information traveling faster than light. Einstein found this so concerning, he dubbed it spooky action at a distance. But if we look at space-time through the lens of this modulus theory, things fall into place. If space-time is born from the quantum world, then closeness in a quantum sense takes precedence over physical proximity. As Hermannick put it, it's like feeling closer to a loved one who's far away than to a stranger living next door. In the quantum world, these non-local connections are totally plausible. Friedel, Lee, and Hermannick have been diving into this groundbreaking idea for the past 5 years, and they're cautiously optimistic about their progress. The appeal of their approach is that it envisions a quantum world with gravity, instead of trying to apply quantum rules to gravity as loop quantum gravity does. The next big step for them is incorporating time into their model. While all this might seem a bit abstract and purely academic, the implications could actually transform our daily lives. Our understanding of space-time affects our grasp of both gravity and quantum theory. As Hossenfelder points out, our current gadgets all rely on quantum theory. So, a better understanding of the quantum structure of space-time could pave the way for advanced future technologies. The reigning theory of space-time, much like any long-standing monarch, might soon be dethroned, and it's high time for fresh contenders. However, it's tough to predict which of the many theoretical contenders will eventually triumph. But when the revolution does happen, it could herald a new era of discoveries for theoretical physics. So, what's the next move for astronomers, scientists, and physicists? What are your thoughts about this? Do you think the James Webb Telescope might be the solution to our problems, or might it just be leaving us with more questions? Let us know in the comments. Stay tuned for more mind-bending videos.